So now we're made it to the module 13, where we're actually going to be solving both exponential and logarithmic equations. So we've looked at both exponential and logarithmic, the properties of both, and we're going to use these features to help us solve these types of equations. So a couple different examples. So we take different approaches depending upon what the equations are. So this first one, when the bases of the exponential function are the same, then because exponential functions are one-to-one, if the base is the same, then the exponents also have to be the same. For each input, there's going to only be one output. Well, these don't seem to be the same, but what you have to do, you have to recognize that 64 can be rewritten as 4 times 4, which is 16, times 4 more. 16 times 4 gives us 64. Okay, so we can rewrite this equation as 4x equals 4 to the third power. And so we use this one-to-one property that exponential functions, each input has only one output. And so that means that this input of 3 has to be the same as this input of x, because this equation is saying they end up with the same y value, right? For 64, this has got to be 64. The only way that can happen is if x equals 3. So this is one way, is getting to the bases of the exponential to be the same, then the exponents will be equal to each other. Let's take a look at another example here. And again, we might not spot this. Oh, how am I going to do this? Well, for this one, we might need some help. So again, the only way with this method is to see if 2401 is some kind of a base of 7. Does it have a base of 7? So how do we do that? Well, we sort of do a guess and check. And again, this is sort of, let's see, I think I can do that if I get out of there. There we go. We're going to keep this. And what I'm going to do is in my calculator, I'm just going to go 7 times 7. That's 49. Well, what if I multiply by 7 again? So notice it took the answer times 7. I got me to 343. Let's try it again. There it is, 2004. So what did I do? I multiplied 1, 2, 3, 4. So 7 to the 4th power is 2401. So with these type of questions, that's what you're looking for, is how can I rewrite this equation, the one side as 7 to some power. And what we're going to see is, this case, it's going to be 7 to the 4. These we've never were asked to memorize exponential tables, or, like we did with multiplication tables, but that's so we kind of use our calculator to get these facts down. After we've done it a few times, what you'll see is you'll start to recognize numbers. Like 343, when I see that, oh, that's 7 to the 3rd power, but it's only because of really teaching this class, to be honest. Because who knows these stuff? And now I might start to recognize 2401 as 7 to the 4th power. And we'll go with green this time. And again, since these are one-to-one functions, this is saying the outputs are equal, so they also have to have the same input. Okay, so we solve that one simply that the exponents have to be equal, x equals 4, using the same base. Okay, if they have the same base. Now, if this had been 2402, we wouldn't be able to do this because these are not equal. We would use some of these other methods we're going to use. Okay, we can also use something, as I introduced earlier, called the log dance, what I call the log dance, and that's converting from an exponential to a logarithm, or a logarithm to an exponential. So let's go ahead and take a look at a couple examples here as well. Okay, So 5 to the x equals 21. There's no way you can make 21 as a base of 5 to some power. That's reasonable. I mean, obviously it does work. It'll be some sort of decimal. But the way we're going to solve this one is to do the log dance. And now remember the exponential function. These two things, you've got 5 raised to the x power. These are interacting together. Equals 21. And when we get the inverse, these two that were together will be on opposite sides. So the base, 5, of an exponential becomes the base of a logarithm. So that's log base 5. And the x has to go up to the other side, and the thing that was by itself, the output now becomes the input into the logarithm. And notice we have solved this for x. Now, if they want an exact answer, this is the exact answer. If we put this in our calculator, we're getting an approximate, right? Because we're going to have to round it at some place, because it's going to be some number with several decimal places. Not quite 2, right? Because 5 to the 2 is 25, so it's a little bit less than 2, but certainly more than 1. 5 to the 1 is 5. 5 squared is 25. Right? This is sort of how we can estimate it. 5 to the first power is 5. 5 to the second power is 25. So we know it occurs somewhere between 1 and 2, closer to 2 than to 1. And we can now also plug this into our calculator. So we're going to go ahead and do that, but notice that this is the exact solution. So if that's what they're asking for, this is what they want. If they want the approximate solution, and we'll just abbreviate it there, solution, that's when we're going to round it. And let's see, we come over here, and multiple ways you can do this, but with the TI-84 calculator, we can use the math function. And then I'm going to go upwards. You can go down, but it's at the very bottom of the list, so a student showed me that this is a shortcut. Go up. And then you see log base right there. And you can actually enter this in. And you'll see the next problems we're going to do, but that's okay. So we put the base of 5. We put in 21. And we enter. And notice it's close to 2, closer to 2 than the 1. It's 1.89. We could round it to 2 decimal places. What I'm going to say is, remember that when we use an exponential, a logarithm, the answer to the logarithm is the exponent that we would put on the base. So when you're using these exponents, it's to be as accurate as possible. I found that about 5 decimal places does it. 4, you get off a bit. But if we go to 5 decimal places, 1, 2, 3, 4, 5. So this 6 is going to become a 7. So I'm going to write this as, I guess I had it set up over here to put the approximate. So I'll just get that one out of there. 1.89167. And again, what you can see is if you take 5 and you raise it, let's see, come back over here, take 5 and raise it to the 1.89167, we're going to get pretty close to 21. We won't get exactly 21, I don't think, but see, close enough that it works. If we go, and I'll just show you this, we'll go down to 1 decimal, or let's just do it to 2 decimal places, 1.89. And this is why I don't round it to 2 decimal places. I'm not nearly as close. Now, yes, this would round to 21, but notice the more decimal places we use, the greater accuracy we get. Okay? So let's return to our lesson. And we'll keep keep working through this. So now we can do the same thing. We're going to stick with the exact solution. You know, if they ask for the approximate, you now know how to plug it into the calculator. But to be able to use the log dance, what we have to do is we have to have the exponential part isolated by itself. This has a 4. We're multiplying by 4 and adding 5. So we have to do some solving first. We have to do some algebra. And remember, with algebra, you always do the opposite operation in the opposite order. So usually we multiply first and then add. So we are going to do the opposite, which is subtract, and then we will divide. And we'll see we'll get the exponential part by itself. That's what we're seeking to do. So plus 5 minus 5 is 0. So we're left with 4 times 3 to the x equals 33 minus 5 is going to be 28. That's kind of convenient. And then we're going to divide by 4. Divide this side by 4. Divide this side by 4. 4 divided by 4 is 1. And so we end up with 3 to the x. 28 divided by 7 is, 28 divided by 4 is 7. See, that's happens to me all the time. It's maybe I think too fast. I don't think so, but anyway. So now we can do the log dance. The base of the exponential stays as the base of the logarithm. So that's log base 3. The x is going to come to this side. The 7 is going to go to that side. So the input of the logarithm is 7. The answer is x. So notice how the answer to a logarithm problem is always an exponent. The exponent is the answer. We have solved. This is the exact solution. If you plug it in our calculator again, we'll get some number. Notice it'll also be 1 point something, because 3 squared is 9. 3 to the 1 is 3. So it's somewhere, so this x is going to be somewhere between 1 and 2. A little bit closer to 2, because 7 is closer to 9, right? So that's how we can think of it. But this here would be our exact answer. And finally, we've got this e function, right? This e to the 7x. We can also do this with a log dance. And now this one, we're starting with the exponentials already isolated. But there's, we'll see there's an extra step here anyway. So the base is the base of the logarithm. So this is log base e. We could rewrite this, and we will, as ln. Okay, it's just because it's one of our special cases. Natural logarithm, we could write this way, but they've got a special value that writing it. The 9 comes here, the 7x goes there. Now this is not an exact answer because we don't have x isolated. We don't have x equals, right? Like we did in, I guess I should box these in. Well, I'll box in the exact solutions. We ended up with x equals, but now we've got 7x equals, and so for this one, it's a little different. We've got to divide both sides by 7. Okay, so for my solution, I'm going to rewrite this as a natural logarithm. So log base e, I can write as ln. Don't have to put a base on it. Well, in fact, can't. This is incorporating the e as the base. Natural log of 9 divided by 7. That's what x equals. Not the natural log of 7, right? Because 7 is just 7. These guys cancel. They become 1, right? So this is our exact answer. And again, that's one way of solving is using the log dance. If we have logarithms already, we can do what I call the reverse log dance and turn them to exponentials, and that will also solve them. So we're going to take a look at a couple of those examples. The reverse log dance. So if I've got this logarithm, right, I can turn this into an exponential, and what we're going to see is that that will allow me to solve for x, allow us to solve for x. So how do we do this? Well, the base of an exponential is the base, the base of a logarithm is the base of an exponential. So that's the base. It's going to have an exponent. What's the exponent going to be? The answer to the logarithm. So notice how there's two items on the left side, one on the right. And so what's going to happen is the two on the left side split, and the one that was by itself now goes up here, and that's equal to the input, so minus 5x plus 9. We now have an equation, well, it still has an exponent in here, but we can actually work this out. 2 squared is going to be 4. And we can solve this equation, just now a linear equation. We would subtract 9 from both sides. 4 minus 9 is negative 5. 9 minus 9 is 0. And then we just divide both sides by negative 5. And we will have to solve for x. This is a factor of 1. This also is a factor of 1. So we get that x equals 1. Now we plug that in. If you put 1 in here, you get negative 5 times 1 is negative 5, plus 9 is 4. So plugging in 1 for x, you see that log 2 of 4 equals 2, because 2 squared equals 4. Okay, so it all works out. And again, we can solve just by using this sort of log dance. There's another way people do is they do an exponent to both sides. That can work too. We'll look at some other ways, but this is to me the cleanest way of solving them, using the sort of the definition of the inverse function. Okay. Now this one we can do the same thing, but again we have to isolate the logarithm first. So we've got more than just a logarithm going on. We've got this negative 7. So we'll divide both sides by negative 7, because negative 7 is multiplying. Right? So this is 1 over here, and this is 2. So we get log base 5 of 4x equals 2. Now with the log dance, we're going to see this becomes relatively easy to solve. So the base of a logarithm becomes the base of an exponential. The answer becomes the exponent, and the input becomes the answer. So that's that log dance. It's just to move them around, right? Following the definition of what an inverse function is. This is the inverse of this, but they will both give us the right answer, right? We've solved. That's how we've been solving. We always do the inverse, right? Instead of adding, we subtracted. Instead of multiplying, we divided. And instead of doing a logarithm, we exponentiate. And again, this gives us 5 squared. We can now do the math. 5 squared is 25. And then we just divide both sides by 4, right? Inverse, right? Inverse functions. That's all an inverse is backwards. 4 divided by 4 is 1, so that gives us x. 25 over 4. We could just leave it that way. It doesn't make too bad of a decimal. 25 divided by 4 is going to be 6.25. Right? 4 goes into 24 6 times. With 1 left over, 1/4 is a decimal of 0.25. So there's another way. And both of these are exact answers because we didn't round. So we should be able to list either one. Okay, so that's, again, using the logarithms, the definition of the inverse, of changing a logarithm into an exponential, and then finishing up and solving from there. Solving means we're getting x equals. What about natural logarithms? Well, they really work the same way. Just remember that the natural log of something is really just a rewritten log base e of something. Okay, these are the same. They're just different ways of writing it. So what we're going to see is we can do a log dance with it. It's just when we have a natural log, our base is e. Okay, so let's do that. So again, we need to isolate the logarithm part. We've got it times 3. So we're going to divide by 3 on both sides. And that gives us that the natural log of 6x equals negative 6 divided by 3 is negative 2. Now when we do this log dance, we just have to remember there's this base e here. So the base of the logarithm, let's change colors, why not, becomes the base of the exponential, right? So there's this little phantom e down here. I have to sort of remember. The answer becomes the exponent, and the input becomes the answer. Or the input becomes the output becomes the input. That's what an inverse function does. That's how they work. So anyway, this is almost an answer. All we have to do now is divide both sides by 6. Divide both sides by 6, and we end up with our final answer that x, right, because this 6 divided by 6 is 1, x equals, I'll flip sides on here, e to the minus 2 over 6. We can rewrite this because a negative exponent, moving it down, we could rewrite this as 1 over 6 e to the positive 2. Both are valid answers. Just if they want not having negative exponents, we can write it this way. So kind of think through those. But this is an exact answer. If we plug this into our calculator, either one of these, we will get a decimal equivalent. Okay, so just remember with natural logs dealing with ln, that it has a base of e, the number, and e is a number. It's not a variable. Okay. Example where we have logs on both sides of the equal sign. So the first thing we want to do here is we've got the logs on the opposite side. We can use logarithm properties if we were to get them both onto the same side. So we're going to work with that. Blue. We'll leave this 1 over here, and we'll simply add the log base 5, x minus 6, this whole thing to the other side. And the reason we can do this is because the logarithms have the same base, and so we're going to be able to combine them using log properties. So a negative and a positive, these become 0 on this side. We get log base 5 x minus 6, that's the positive one, minus log base 5 x plus 2, and that's all equal to 1. Now that we are subtracting two logarithms, we can combine these using that property that subtraction becomes division. So this becomes log base 5 x minus 6, the input there, divided by x plus 2, which is equal to 1. And now we can change the logarithm into an exponential by doing what I refer to as the log dance. The base remains the base. The answer of a log question, remember, is an exponent. So that gives us that 5 to the first power is now equal to the inside part of the logarithm. So we're going from a logarithm equation to an exponential equation. X minus 6 divided by x plus 2. We put parentheses, we don't have to. And so now we can solve this. Okay, so we've got the logarithm out of here. The parentheses are actually no longer needed, and we can finish solving off with this thing. Get rid of the fraction by multiplying by the fraction's denominator, x plus 2, on both sides. Again, when we've got an equal sign, we can multiply both sides by the same thing. So x plus 2 goes away. We can distribute this 5 to the first power, which is 5. And so on this side, we will get 5x plus 10. So right, I distributed. On the other side, we just have x minus 6. And now, kind of like what we did with the logarithms, isolating them to one side, we want to isolate the x's. So we can subtract x from both sides. And if you want to in one step, we can kind of see, well, I'll do it in 2 steps, but you could also subtract the 10 at the same time to get it to the other side, but we'll do it in 2 steps. So this is 5x minus x is going to give us 4x plus 10. X positive x minus x, that's 0. So we get a negative 6. And then now subtract 10 from both sides. And that's going to give us, that will cancel. I guess I think I have enough room here. I've got another example below. We have 4x equals negative 16. And then we can divide both sides. I'm just going to bring it up here. Just copying it over. We can divide both sides by 4. Then we get x equals negative 4. Oh, we're done. Really? Well, we have to check, though. Remember, for any input into a logarithm, it has to be a positive number. And so in this case, x equals negative 4. Let's check if it'll work. Well, if I put it into this logarithm, I'll have negative 4 plus 2. That's going to give me a negative number. I get negative 2 inside of a logarithm. So it's not, it doesn't work here. I don't even have to check over here. I could. Negative 4 in here, negative 6, I'm going to get negative 10. That's not going to work either. So it doesn't work in either one, but the fact that it didn't work in one of them means that there is, not x equals negative 4, but there is no solution here. Now, it might have felt like a lot of work to go through to find that there is no solution, but it just is what it is. Okay, so that's that one. Here's another example where we have logarithms on both sides. This is a natural log base e. But in this case, we have one side where there's the same logarithm. And so we can do this slightly differently. We can use the properties of logarithms by combining these two. So this is natural log of x minus 6 minus natural log of 2. So that will become natural log x minus 6 over 2 equals natural log of 20. Now we can use another property. We don't have to, we could bring this over, subtract it over and combine it again. But we can also use the property that when a natural log equals a natural log, since they are one-to-one functions, natural logarithms in general are all one-to-one functions. And so what that means is if the outputs are equal, that's what's happening here, then the inputs are equal. So we are able to just jump to x minus 6 over 2 equals 20. Whenever we have the same base logarithm on both sides, in a way it's kind of like they cancel, but it's not quite. It's the fact that this property that they are one-to-one functions. Since the outputs are equal, one-to-one means that the inputs also have to be equal. Okay, and so for this one we go ahead and solve for x. So we will multiply both sides by 2 to get rid of this denominator. So 2 divided by 2 is 1. 2 times 20 is 4. So we've got x minus 6, 40. Sorry, 20 times 2, 40. And then we can add 6 to both sides. X equals 46. Again, we want to check it. If I put in 46 here, minus 6, that's going to be okay. And we could even go ahead and do a check. So natural log of 46 minus 6 minus the natural log of 2 equals the natural log of 20. 46 minus 6, that's going to give us the natural log of 40 minus the natural log of 2 equals the natural log of 20. Again, combining logarithms, we could have natural log of 40 divided by 2 equals the natural log of 20, and therefore the natural log of 20, 40 divided by 2, is equal to the natural log of 20, which that is a true statement. We don't have to really go in further. It checks. So this time we can say yes, our answer is x equals 46. So that brings us to the end of our direct instruction for Module 13, solving exponential functions. You can also do this with Desmos and graphing. You could play with that, but these are methods of using the log dance, using logarithms to solve exponential functions, and then also using exponentials to solve logarithmic functions. Notice they got the x either out of the input in the case of a logarithm, or they got it out of the exponent in the case of an exponential. So that idea of using inverse functions, the definition of an inverse function, that it's just a reorganization of what we're doing. Subtraction, its inverse is addition. Addition, subtraction. Multiplication, inverse is division. Division, multiplication. So those are inverses. Exponentials are the inverse of logarithms. Logarithms are the inverse of exponentials. They have a great partnership in working together. All right. So go ahead and get working on the Module 13 activities. Remember, we have our online tutoring available, instructor office hours, and continue working with peers through the discussion forums.